Okay, so this is the cooler equation, or more useful one than that rationale one, but because this is what's going to get us to like a characteristic pump performance curve. The other one is more about to see, well, what could, definitely what's going to get me at least more than can calculate better values. So first things first is you take. I think you all already remember this formula. I'm going to use the ideal subscript because you should have an idea that everything we're doing right now is fake and it's not going to happen because it's too idealized, but it's an idea. So it's idealized so you can get an idea. So that's where that subscript I comes from, or H subscript A is what's actually happening in the pump. So we already know that this is right. This you can equate this to this rho G cubed H, which is equal to G. Okay. So then this just implies that, well, so I can actually get, right, an ideal head rise just based on this expression here, right? So then we're trying to get our first iteration of what is the ideal head rise based on a pump's performance. And it's nothing but the exact same equation but with something like this, right? So not that cool, only that you can play with the value of gravity. The other important thing is that, remember that in terms of efficiencies, which we will get into, right, this is the shaft power actually transferred to the fluid, right? So this is right. Okay, this is actually always sort of less than, right? Some of you did efficiencies for your pumps in the projects, which which was nice. It's good work. But here's actually where we need to consider that, because the idea that the actual power transfer to the fluid is always going to be less than the actual power of you running the motor, because there's just energy losses of heat, acoustics, etc. But in the most simplified setting, just understand that, make an efficiency plot, good to go. Because engineers simplify everything. Okay, so almost there. I think, yeah, I'm pretty close. So even more now, we're going to look at this head, ideal head for a pump. Remember, there is a value of gravity right there. Okay, so same thing. Let me draw this control surface again. Angular velocity like that. And you have these two and then on this one, parallelograms are a nice Lily out one. 2, beta 2. You probably can't see because I have what I have. Okay, so then look at these parallelograms, and now we're gonna now the whole point is we want to write out the V, this term. We want to get a handle on actually what these these theta components actually are. And we'll do it again with some geometry. So if we just look at this, right, the same relation will hold for both of them, but bear with me. You have this W. This one is a U. This one's my V. Okay, here is this beta. It's the angle created from this projections tell me that this is velocity in the r, this is the velocity in the theta. Right? So maybe you hopefully you can see it's better done in the notes. This is actually an angle, right? Projected outward. W. So sort of this is what I'm trying to get, that VR and then this V theta. Okay. So here we have a cotangent. So make sure I can see. Yep. So what comes out of that diagram is this geometric relationship that VR cotangent beta 2, or any beta of this parallelogram, right, is equal to u minus v theta. That comes from drawing this parallelogram. The fact that you have, I can express this radial, I can express this absolute radial component in terms of these two components right there. Okay. So I think I have extra credit to just do that geometry and show, right, and just show how that pans out. Okay. What else? Next, using this, we have to make some more assumptions on this equation we had before. The first one being this. I'm going to say this term is essentially 0. So I only am left with the second term, or the V2 and the V theta 2. So, what are some rationales that we should say that? Well, intuitively, it should probably make sense just because the one component, right, the V1 component was what was involved in this part right here. And I know that I've decelerated fluid a bunch and it slowed down, then had to turn into the XY plane, then move. So then that really, this has to be basically slower than what's going to be happening at the end. It's not really intuitive, but the idea, you just kind of can see that happening. But with just these variables in mind, well, definitely what I would know is the radius, right? Because here I have a little r1, here's, right, definitely a much bigger r2. And that's definitely proportionality for this thing right here. So, right, then the question you have, let's just stop right there. I'm sorry, I was looking at my other reasonings, but I think that's enough, right? Just that the idea that these radiuses are actually much less, so I'm pretty varied in saying this value right here. So that makes a pretty simple now term, because now I'm just saying that this equation is just that, because I knocked off the last term. Also, you can also say that like I've divided by 10-ish. So more reasons to kill that last term, which is a swirl velocity, some would say, or it's just negligible in comparison. Okay, so what we end up doing is using that cotangent formula did in the notes and get this relationship. Beta 2, because this is the out, right? This is the exiting. Beta 2's exit. 1 is in. And then 2 pi, I have an R2 of B2 G Q. Not squared. That's why also this is super wrong. And this is just right, and this just comes from comes from velocity areas, or it's a projected area. So this R and B is widths of impellers, etc. Right. So that's the idea that this would be a height. In terms of if I'm looking at the cylindrical side, this B is sort of the height of the impeller or the width of your turbo machine section. And that's the end of this section, really, because we've arrived at a way to estimate the head rise based on what? Based on my designed pump parameters. I have U2 there. U2 involves radius, involves angular velocity, so I can use that. I have a beta term here, beta totally designable. I can make it as curvy. I can make other ways as possible. I can make this positive if I change the cotangent. There's cool questions on that. I definitely have control over these radii here as well. I could be on Mars or the moon, and then I have Q. So always, right, you should get a sense that that's the goal for derivations, right? You want to get a requirement involved in things that you can design, rework physics to do that. So I think this is a fantastic example of achieving that, which is why I maybe took longer doing this one than any other mathy thing I've done, just because it's so complex, but we went from really complex pictures to simple pictures to get at something I can use as an engineer. Okay, always with an equation. They're kind of cool, but in the end, all that matters is a plot, because the only thing that's to look at an equation these days is a computer to give you the number from it. Okay, so what this equation is a line. Right? You can just see that from the functional form. Right? What's the slope of that line? Well, you can just look at that equation again. We'll tell you it's negative U2. And that's your ideal pump curve. It's a line, there's no curvature involved in it, and that's based on all the idealizations that we came up with. All right? And there are tons of reasons that there are losses involved of why it doesn't look like this. In reality, right, the real pump curves look like this. Everything not on here is what we attribute to something called losses. Right, just losses in the pump. You just, same as like, think of it as just a ton of K components involved on the inside of geometries of whatever happened to the black box that was your pump. But that's where these losses are attributed to. There's two kinds of losses. There's one that is split up like this, where this is frictional losses. So this strip right here can be rationalized and can be described in terms of that external flow stuff we did. Right, and it's going to get bigger with velocity just for all the same reasonings, which is super cool, super great thought exercise to rationalize where losses are coming from. Right, even knowing why it has to go to zero, it just makes this right. It's just making the slope. This looks like it might look like a line on your on. I was trying to have a curve there as well, so it turns it quadratic is another important thing to look at. But then there's also just these other ones involved. And actually, I should do this for sake of what they usually look like. Usually kind of here, it does kind of get really close to the ideal in terms of the actual pump rise. We don't see commonly like these. We don't see commonly this ideal curve being like enormously far apart from the actual. But it's just the endpoints that are really, really wrong. And then these other losses happen. There's a little. So these are the other losses. And there are many, many reasons for these other losses, which I've listed in the notes. Yes. So maybe I'll make you read those. Maybe you all do read them. So then this pump is the one that really you design off of. This is the HA. This line is this ideal pump. This is the actual one. These are what they look like. Some teams actually did for this project, and some people, they used pump curves And I don't know if they really knew what they were. They just looked at like they used some software to like intersect things. So maybe now you can appreciate that, like what those curves are really saying. Sometimes they even approximate these things as well. And that is your pump performance curve, and it involves just so much can come from this curve based on relating the flow rate of your pump to the actual head rise it can perform for you. So this idea of there is a maximum flow rate a pump can do, right? There's a maximum amount of flow it can do, and at that point you don't get any head rise to it, and that's conceptually that's hard. That's initially hard to grasp. But I want you to think about it based on all the equations and things we've done and how to get to this expression. Why should that be the case? The other one being, if you have no flow rate, if you have zero flow rate through your pump, you have a positive head rise. Maybe that's the easiest, right? The easiest pickings ones, but again, there's a lot of reasonings that come through here. It's also important to remember the fact that at low flow rates, the ideal is wrong, and at large flow rates, the idea is very wrong. But let's say at like medium flow rates, the ideal is not too wrong. So it's a good first starting thing. So extra credit, I think I had extra credit as well. I would say extra credit measure right? Kind of fun, right? So then take apart some turbo machines in your house and try to measure any of these components just any way you can. Take some pictures. This one's hard, the U, because you actually need to figure out what that angular velocity is. But if it's slow enough, you can go like 1, 2, 3, calculate every 10 times, or count every 10 times and divide. There are ways to do it, but it's a fun exercise, and then you can actually make a plot of your own home turbo machinery and see what that pump equation is. Importantly, though, right, whatever these HAs are, right, HA usually just looks like some negative coefficient and then sort of Q to some alpha. That is, right, they all can be modeled that through data, etc., or any sort of data, etc. In fact, you'd actually have it something that looks like this. Right? It could even be like a combination of polynomial terms, right? So, in fact, right, you could just do as many as you want, right? You could just have right, so you can approximate the actual one based on data to some arbitrarily more accurate polynomial. There's a best fit involved with something like this. But these A's can actually be turned into functional forms, and they really are going to follow this way. The easiest way is to use polynomial fits. You could do like a cosine as well, but cosines also polynomials. You could do like a tangent. You could do like the first half of an arc of arctan H. But again, that's also a polynomial. Like everything is a polynomial in terms of approximation. So, right, M could be really high. These K's, you can figure out what they are through a best approximation, and then the Q's, it would tell you what the bests are. Question being, which ones do you want to model better? Those are just ways, though, that you could actually like figure out what your HA is and get it into a workable math form to then give to Python, or not have to use these graph intersection tools. I've gone far too long on that, so I need to do another video.